Welcome to Astronomy Daily, your gateway to the latest cosmic revelations. I'm your host, Anna, and today we have an episode packed with exciting space news. We'll kick things off with an unexpected launch delay that saw a crucial solar wind mission temporarily grounded, and we'll uncover the surprising reason behind that scrub. Then prepare to meet an ancient interstellar visitor, Comet 3I Atlas, and discover how it was accidentally spotted even before its official discovery. Finally, we'll provide practical tips for safely observing and photographing our very own star, the dynamic sun. Let's dive in. Let's start by delving into some recent launch news, specifically a SpaceX Falcon 9 scrub at Vandenberg Space Force Base that caught many off guard. What initially looked like a straightforward hold turned out to be a bit more complex. SpaceX was all set to launch tracers, NASA's latest mission to study solar wind and its impact on Earth, from Vandenberg's SLC-4E. The booster was even planning a return to launch site landing. Everything seemed to be going smoothly in the final countdown, right up until the hold call came in, indicating the launch was paused and, for Falcon 9, scrubbed for the day. The initial announcement cited FAA airspace concerns, which isn't entirely uncommon, as a range can go red if a boat or plane enters the exclusion zone. However, this time the reason was far more unusual. The Federal Aviation Administration, or FAA, confirmed that the airspace concerns weren't about a specific aircraft, but rather the Air Traffic Control Center monitoring those aircraft. This particular center, the LAARTC, is responsible for a massive flight information region covering Southern California, where Vandenberg is located, along with parts of Nevada, Utah, and Arizona. A regional power outage in the Santa Barbara area caused communication problems for the LARTCC. This meant they couldn't verify, or perhaps even tell SpaceX, whether the range was clear for launch. Without that crucial green light, SpaceX had no choice but to scrub the Falcon 9 launch due to the unacceptable range configuration. While this specific launch faced an unexpected hurdle, another attempt was penciled in for the very next day. Interestingly, despite this West Coast snag, SpaceX did manage a successful launch just hours later from Cape Canaveral Space Force Station in Florida. Two satellites for SES-owned O3b networks, mPOWER 9 and mPOWER 10, lifted off during their second launch opportunity. This particular Florida launch had its own set of challenges, as its first attempt the previous day was also scrubbed, though that was due to weather conditions rather than range issues. It just goes to show the dynamic and often unpredictable nature of space operations, with various factors from power outages to weather playing a role in getting these missions off the ground. From one dynamic event to another, let's now turn our gaze to Jupiter's intriguing moon, Europa. New observations from the James Webb Space Telescope are painting a vivid and frankly quite chaotic picture of its icy shell, revealing it to be a dynamic world far from frozen in time. For decades, scientists often pictured Europa's frozen surface as a still, silent shell, but these new findings are completely changing that perception. According to Richard Cartwright, a spectroscopist at Johns Hopkins University's Applied Physics Laboratory and lead author of this new study, the surface of Europa is likely quite porous and warm enough in certain areas to allow ice to rapidly recrystallize. This suggests a level of activity we hadn't fully appreciated. Even more exciting is what this surface activity reveals about Europa's subsurface ocean, regions known as chaos terrains, highly disrupted areas where blocks of ice appear to have broken off, drifted, and then refrozen, are proving to be incredibly valuable. They act as potential windows into Europa's mysterious interior, hinting at ongoing geological processes. The study specifically focused on two regions in Europa's southern hemisphere, Terra Regio and Pauis Regio. Terra Regio, in particular, has emerged as one of the moon's most intriguing areas. The Webb telescope's observations detected crystalline ice not just on the surface, but also deeper below, which challenges previous assumptions about how ice is distributed on Europa. By measuring the spectral properties of these chaos regions using remotely sensed data, scientists are gaining crucial insights into Europa's chemistry and, significantly, its potential for habitability. Ujjwal Raut, program manager at the Southwest Research Institute and a co-author of the study, emphasized that their data strongly suggests that what they are observing must be sourced from the interior, possibly from a vast subsurface ocean nearly 20 miles or 30 kilometers beneath Europa's thick, icy shell. To better understand this, Rout and his team conducted laboratory experiments. They studied how water freezes on Europa, where the surface is constantly bombarded by charged particles from space. Unlike Earth, where ice naturally forms a hexagonal crystal structure, Europa's intense radiation disrupts this, causing it to become amorphous ice, a disordered, non-crystalline form. These experiments were vital in demonstrating how the ice changes over time, offering clues about the moon's surface dynamics. When combined with Webb's fresh data, these findings add to the mounting evidence of a vast, hidden liquid ocean beneath Europa's icy crust. Cartwright pointed out that in these same fascinating regions, they've also found strong indications of sodium chloride, essentially table salt, likely originating from that interior ocean. Furthermore, they've seen some of the strongest evidence for carbon dioxide and hydrogen peroxide on Europa. The chemistry in these specific locations is truly bizarre and incredibly exciting. These fractured surface features strongly suggest geologic activity is pushing material up from beneath Europa's icy shell. Webb's near-spec instrument is particularly well-suited for studying Europa's surface because it can detect key chemical signatures across a wide range of infrared wavelengths. This includes features associated with crystalline water ice and a specific form of carbon dioxide called 13CO2. This is significant for understanding the moon's geological and chemical processes. The team detected higher levels of carbon dioxide in these areas compared to surrounding regions, leading them to conclude that it most likely originates from the subsurface ocean rather than external sources like meteorites, which would result in a more even distribution. Given that carbon dioxide is unstable under Europa's intense radiation environment, these deposits are thought to be relatively recent and directly linked to ongoing geological processes. The evidence for a liquid ocean underneath Europa's icy shell continues to grow, making this an incredibly thrilling time for planetary science. The discovery of carbon-13, an isotope of carbon, further deepens the mystery. As Cartwright noted, it's hard to explain its presence, but every road leads back to an internal origin. This aligns with other hypotheses about the origin of carbon dioxide detected in Terra Regio. This new study also comes at a perfect time, as NASA's Europa Clipper mission is currently en route to the Jovian moon, with an expected arrival in April 2030. The spacecraft will perform dozens of close flybys, gathering critical data about the hidden ocean, building upon the incredible insights from the James Webb Space Telescope. Now let's shift our focus from the icy moon Europa to an even more distant and ancient visitor, Comet 3I Atlas. This celestial object holds a special place in astronomical history, as it is only the third interstellar object humanity has ever observed entering our solar system. The previous two, one I Oumuamua in 2017 and two I Borisov in 2019, have already made their grand exits, but 3I Atlas is still giving us plenty to talk about. What makes this comet particularly captivating isn't just its interstellar origin, but also the serendipitous way its earliest high-resolution images were captured. Get this. The Vera C Rubin Observatory, a powerful new facility designed to scan the universe, actually took pictures of 3I Atlas before it was even officially discovered. During its science validation phase, the Rubin Observatory just happened to be pointing at the right part of the sky where 3I Atlas was located. Unbeknownst to the operators, it snapped images of the comet between June 21st and July 7th, even a few days before the telescope officially released its first look images to the public. These observations are incredibly important because they represent the earliest, highest resolution images we have of this rare interstellar visitor at that time. The observatory's 8.4-meter Simoe survey telescope, combined with its 3.2 gigapixel legacy survey of space and time camera, provided unparalleled detail. Adding to the excitement, the Hubble Space Telescope also caught its first glimpse of Comet 3I Atlas. These Hubble images confirm the comet's puffy coma, a cloud of gas and dust surrounding its nucleus. The arrival of 3I Atlas has really ignited a period of intense study for astronomers, with many instruments now attempting to get a good look at it since its initial spotting on July 1st, 2025, by the Atlas Survey Telescope. Recent research suggests that 3I Atlas could be even more exciting than initially thought. Its trajectory through our solar system indicates it comes from a region of the Milky Way that is older than our own 4.6 billion-year-old solar system. With an estimated age of 7 billion years, 3I Atlas holds the title of the oldest comet we've ever seen, offering a potential window into the earliest days of planetary systems far beyond our own. The images captured, especially those from Rubin, reveal a comet that largely behaved as expected, confirming its cometary nature with a clear coma of gas and dust. Interestingly, the apparent size of its coma grew by about 58% during the observation period as it continued to approach the sun. But here's where it gets truly unique. It had a sunward-pointing tail. This unusual phenomenon, explained by what's called anisotropic dust emission, is relatively rare but has been observed in other comets. It could be due to the slow ejection of large particles that aren't pushed back as quickly by the sun's radiation pressure, or perhaps a rotational axis that nearly aligns with its orbital plane. While 3I Atlas hasn't shown any signs of non-gravitational acceleration, unlike 1I Oumuamua, astronomers will be watching closely as it approaches its perihelion in October, though it will unfortunately be blocked by the sun from September through December and won't be visible during that crucial period. Nevertheless, the data from 3I Atlas is already incredibly rich. Optical and near-infrared spectroscopy has revealed that it's an active interstellar comet containing abundant water ice with a dust composition similar to D-type asteroids, space rocks rich in organic molecules, silicates, and carbon. This kind of detailed insight helps us paint a more intimate picture of planetary systems beyond our own. The Vera C Rubin Observatory, which inadvertently gave us these early views, is expected to discover between 5 and 50 more interstellar objects as they zip through our solar system over its decade-long survey, promising a future filled with even more cosmic surprises. From ancient comets to cutting-edge observatories, space constantly offers us new wonders to explore. But sometimes, the most extraordinary cosmic sights are right here in our own solar system, if you know how to look for them. For our final segment today, let's turn our attention to our very own star, the sun, and unlock the secrets to safely and effectively photographing its intricate details. Most of us have probably taken a picture of the rising or setting sun, but those images typically show an overexposed ball of light. That's because even with the lowest camera settings, the sun's surface is simply too bright for standard photography gear to resolve any detail. To truly capture our dynamic local star, you need specialized equipment and a deep understanding of safety. First and foremost, safety is paramount. Never look directly at the sun without certified solar eclipse glasses, as even brief exposure can cause permanent eye damage. When photographing, if your camera has an optical viewfinder, avoid looking through it. Always use the digital display, as some filters designed for cameras aren't safe for direct eye observation. To successfully photograph the sun, you must significantly reduce its effective brightness. The primary tool for this is a neutral density filter, which attaches to the end of your camera lens. These aren't your everyday filters. You need one specifically designed for solar photography, capable of blocking out an immense amount of light, over 99.9% in fact. These specialized filters ensure you can resolve details while protecting your camera sensor. Different filters allow you to capture different layers and features of the sun. A white light filter reduces intensity across all wavelengths, revealing the sun's surface, known as the photosphere. With this, you can clearly see sunspots, which are cooler, darker regions caused by intense magnetic fields. For even more detail, particularly of features in the sun's atmosphere above the photosphere, you'll want to use specialized filters like H-alpha or KK. H-alpha filters, for instance, capture light emitted by hydrogen plasma, making the sun appear red and revealing structures like filaments and prominences. Filaments are twisted magnetic structures seen against the sun's disk, while prominences are the same structures seen dramatically arcing out from the sun's edge against the dark backdrop of space. KK filters, on the other hand, filter light from calcium plasma, showing a different perspective of the chromosphere. If you're feeling ambitious, you can even photograph the sun with a telescope, either by mounting your camera to it or using a dedicated solar telescope. These setups often come with internal filter systems designed for detailed solar observation. By experimenting with these various filters and understanding their unique capabilities, you can move beyond the simple overexposed disk and capture the true, ever-changing nature of our star, revealing its fascinating sunspots, fiery prominences, and intricate filaments. Again, a final reminder, always think safety first and never look directly at the sun. And that brings us to the end of another fascinating journey through the cosmos on Astronomy Daily. Thank you for joining me, Anna, as we explored everything from unexpected launch scrubs and the hidden depths of Europa to ancient interstellar comets and the art of photographing our own sun. If you enjoyed today's episode and want to delve deeper into the wonders of the universe, be sure to visit our website at astronomydaily.io. There, you can listen to all our back episodes and become a true astronomy completionist. And don't forget to subscribe to Astronomy Daily on Apple Podcasts, Spotify, YouTube, or wherever you get your podcasts so you never miss an update. Until tomorrow, keep looking up.